A very good afternoon to everyone present, and I warmly welcome you all for the eighth day of online GATE training program 2022. And today we have two sessions. And to begin with, the very first lecture is going to be delivered by the very well known person in the field of geotechnical engineering, Dr. S.K. Prasad sir, our HOD, and the topic is foundation engineering. Dr. S.K. Prasad is the professor and head of civil engineering at Vidyavardhaka College of Engineering, VVCE, Mysuru. He worked for 32 years at Sri Jayachamarajendra College of Engineering, Mysuru, and 3 years at MS Ramaya College of Engineering, Bengaluru. He obtained his bachelor degree in civil engineering from the University of Mysore, securing first rank and 4 gold medals in 1982. He obtained his master degree in geotechnical engineering from Indian Institute of Technology, Kanpur in 1985 and doctoral degree in 1996 from University of Tokyo. He was a visiting assistant professor at Asian Institute of Technology, Thailand for January 2006 term. He has published over 175 technical papers in national and international journals and conferences, guided over 70 master's dissertations, and guided 3 doctoral students. Presently, 3 more students are working for PhD under his guidance. He has completed several sponsored research projects from JSS, MFE, AICTE, and DST. His areas of research interest include earthquake, geotechnical engineering, and performance based design. A very warm welcome to you, sir. And with this, I request you to kindly take over the session, sir. Thank you.
Thank you, Professor Anjan, for your nice introduction. It's always a pleasure to speak to people about geotechnical engineering, and I believe this is my third lecture in the GATE training program for GATE 2022. I have been dealing with foundation engineering. I mentioned in the first class itself that one of the biggest focuses in foundation engineering is foundations, shallow and deep foundations, as well as the bearing capacity problems. So we dealt with majority of bearing capacity problems in the past 2 lectures. I was actually dealing with foundations. So let us continue from where we left and go further talking about foundations. So in today's class, I'll be dealing with shallow and deep foundations and their design, their parameters to be considered in the design. So I hope I should be able to share the share. Should I say, what should I say? Just a minute. Share. I may need some help here. Is it stop screen? Should I say stop screen? Share screen. Okay. Now it's okay. Okay. Yeah, Professor Anjan, you can let me know whether my screen is visible.
Yes, sir, it's visible and audible, sir.
Okay, then. So, as mentioned, I'm into the lecture 3 now. Well, just to recap on what we dealt with in the last class. Friends, foundations are the most important components of a building. They are the ones which hold the entire load from the structure and transfer smoothly to the soil in such a way that neither the foundation nor the soil fail. Okay? And we have 2 types of foundations already dealt with, shallow and deep foundation. When do you call a foundation as shallow? whenever the depth of foundation, as you see here, is smaller than the width of foundation. Or other words, df by b, that ratio is less than 1. Please note that in shallow foundations, we assume that the entire load is transferred to the soil at the base. Therefore, soil at the base is resisting the load. That means soil in the neighborhood here and here, its presence is neglected. Only the base portion is taking the load. And the neglect here is okay. We are on the conservative side. And since it is shallow foundation, the depth is also small. Given a choice, we should always go for shallow foundations. So wall footing, isolated footing, combined footing, strap, strip, and mat, or the shallow foundations in the same order of difficulty. So you go for mat foundation only when all other shallow foundations are not possible. And naturally, raft or mat foundation is the costlier one. And then only when we cannot provide shallow foundations, the situation at the site is not adequate, the kind of load coming from the structure is heavy, then we have to go for deep foundation. I have mentioned to you that pile and well or caisson are the two important deep foundations. Today, we also have piled raft foundation, which is becoming more and more popular, which is a combination of pile foundation and raft foundation. And these are some of the different shallow foundations. As I mentioned, the simplest one is isolated footing. Naturally, given a choice, we should go for it because it is economical, easy to construct. You don't require much time. You don't require sophisticated equipment. Even design is easy. The soil exploration also need not be very elaborate, but only when it is not possible to go for isolated footing, we have to go for higher order foundations. I dealt with combined footing in my last class and mentioned to you some of the very important reasons for the designer to go for combined footing. Maybe property line restriction, overlap of stresses due to heavy column loads, spacing between the columns being small, or SPC of the soil being low, scale of differential settlement, importance of the structures, and designer's wish are some of the important issues which will promote a designer to shift from isolated footing to combined footing. We also solved a simple problem last time. It was required to determine L. Basically, the main concept we use is that the centroid of the area of the footing coincides with the CG of the loads. When you do so, the pressure on the ground will become uniform. So basically, our objective is to keep the pressure uniform as much as possible. So given everything else, L was supposed to be determined, and it was determined in the previous problem. As I said, the concept is that the pressure distribution at the base is uniform. It can happen only when the CG of the loads coincides with the centroid of the area of the footing. Well, when you cannot go for combined footing, you will look for strip footing. Even when it is not possible, you go for raft foundation. I say raft is a complete shallow foundation. It's going to eliminate majority of the problems. Given a choice, you should go for raft foundation, which also enhances the stability of the foundation. Of course, it is more expensive than isolated footing, combined footing, and so on. But it will solve many of the problems. So we talked about the first 5 issues and said that you go for combined footing instead of isolated footing on these 5 issues. I'm not going to repeat the same. Okay. In addition, these are the other 3 additional issues which will make a designer to go for higher order foundation like raft foundation. One is groundwater table fluctuation. Whenever groundwater table is likely to fluctuate from near the ground level to a lower level, it is preferred that we provide a raft foundation which will be solid one. If not, between the foundation, water will rise. Naturally, it's going to cause unpleasant situations under several circumstances, and many a times you don't want the groundwater to go into the foundation area. So if such is the situation, maybe raft is one possible solution, because you seal the bottom. Even if the groundwater tries to rise, there is no scope, because the bottom is sealed. It can only penetrate through the sides, but not from the bottom. So whenever there is a fluctuation in groundwater table, many a times designer wishes to go for raft foundation. Another important reason is provision of cellar flow. For various reasons, designer may have to provide a cellar flow. Maybe they want to increase the number of floors. Maybe height is restricted, therefore, they want a few cellar floors for car parking or so. Under that situation also, the designer goes for raft foundation. Another important issue is settlement. You know that, settlement is one of the important problems in soil. Different soils experience different kinds of settlements. And when they settle, they also cause settlement of the foundation. And hence, the entire structure will be under, a questionable situation. We don't want settlement to be maximum. We want the settlement to be well within the tolerable limits. Sometimes settlement may be more at some places, less at some other places, and so on. When you have a situation like this, in order to balance, in order to provide more or less, uniform settlement, you need a solid slab at the base, and that is when you resort to raft foundation. Uh, I just would like to add here that these are the three major issues which will force a designer to go for a foundation. One is, as I said earlier, settlement. Permissible settlement as per the Indian standards, okay, 6403 you can take, for different types of soils is given here. One is the maximum settlement and another is differential settlement. Both of them should not exceed the tolerable limits. Naturally, you can allow higher level of settlement in clayey soil because they are more flexible. But in sandy soil or stiffer soil, it is better that permissible limits of settlement are well within tolerable limits, lower value. The other important reason is when you have an area, available area, and then you need to provide isolated footings. You find out the total area of isolated footings, and if it exceeds 50% of available area, you go for raft foundation. So to explain this, I have just taken a simple case study. Case one, you have a ground which is 10 meter by 15 meter. In this, you need to provide these 12 columns. Let us say each column, if you want to put isolated footing, the size of the isolated footing on each column is 2 meter by 2 meter. Now, the total area of the plot is 15 into 10 or 10 into 15, 150 square meter. And if we consider isolated footing of 2 meter, 2 meter by 2 meter size, then there are 12 such columns. Therefore, 12 into 2 into 2, that is 48 square meters. 48 square meters is much less than half of the available area. Therefore, in this case, isolated footing will be sufficient. On the other hand, you consider a situation you have 6 by 9 as the plot area, and you have 12 columns again. Each column is supposed to have 2 meter by 2 meter width of isolated footing. Therefore, in this case, the total area of the plot is 54 square meters, and each isolated footing will be 2 by 2 by 12, that is 48 square meters. 48 square meters is much higher than half of the area of this. Therefore, you cannot go for isolated raft foundation. Isolated footing here. The only foundation you can think of is raft foundation. So instead of individual isolated footings, here you are going to connect all of them and put them on one raft, whose size may be approximately close to 48 square meters. So it may be 5.5 by 8.5. So try to see to it that you provide an isolated raft foundation like this. The other important reason for somebody to go for raft foundation is you want to increase the height of the structure. You want to have, let us say, 3 more floors. But then the capacity of the soil is low. Then you may have to go for a deep foundation like pile foundation. The other alternative is you excavate, 1 floor area from the ground surface. When you do so, you are removing that much of muck. So even if you assume that the weight of the soil removed will be is, if you assume 18 kilonewton per meter cube for about 3 meter height, so 18 into 3, 54 kilonewton per meter square. Thumb rule is that for every increase in floor, approximately the additional load is 18 kilonewton per meter cube. Because you have taken up cellar, you have removed this much soil, approximately equal to 54 kilonewton. Therefore, you will be in a position to increase 3 more floors. So for every 1 floor of cellar, you can probably build 3 more floors on top of them. And that's what I have tried to say here. So you have, let us say, 4-storied building. You want to make it 7-storied. It is not possible with the available resources, with the available soil condition. So what you do is you excavate, soil worth equal to, 3 meters of depth. And once you excavate this much, you have a cellar floor available for you. And because you have removed 3 meters of soil, approximately over an area of 1 meter by 1 meter, 18 kilonewton is the load which is removed. And hence, you can add 3 floors, each of 18, which means, totally 54 kilonewton per meter squared is the additional area load which it can take. And hence, provide you with a situation where you have a stable building. Therefore, instead of maybe 4 floors, you are going to make it 8 floors, including 1 cellar. So I had solved this problem earlier, but I just want you people to again understand 4 columns of building are located within a plot size of 10 meter by 10 meter. This is 10 meter, this is 10 meter, 4 columns. Expected load on each column is 4,000 kilonewtons. Allowable capacity of the soil is 100 kilonewton per meter square. What is the best possible solution? Please note that each of the column has 4,000 kilonewton load, therefore 16,000. And area available is 10 meter by 10 meter. 16,000 by 10 by 10 will give you 160 kilonewton per meter square. But maximum allowed is 100, and 160 is much, much higher than 100. Therefore, none of the shallow foundations will be sufficient. You need to go for pile foundation. Let us talk a little about contact pressure. As the name itself indicates, it is the pressure at the contact. Contact between what and what? It is the contact between the footing and the soil. It is the contact between the foundation and the ground below. So, the contact pressure is the actual pressure which is transmitted from the foundation to the soil. Please note that we assume that contact pressure to be uniform in our design, or we may assume it to be varying uniformly. This is only for our convenience. So it's the actual pressure which is developed maybe by the foundation soil at the base. And please note that depends upon the rigidity of the footing, how flexible the footing is or how rigid the footing is, type of the soil, and then the depth of embedment. So extreme soil conditions, purely clayey soil and purely granular soil. If the footing is flexible, then the footing is likely to experience the bending. And in clayey soil, interestingly, you see that the footing will experience a bending, something similar to this, like this, with more amount of settlement seen near the center than at the edges. And the pressure, the contact pressure is going to be uniform. On the other hand, if it is granular soil, you will see less pressure here, and the footing will experience a bending, something like this, more bending on the sides. And if you see the other extreme, that is when you consider the footing to be rigid, you will see that footing is rigid, it doesn't bend. The contact pressure is not going to be uniform. Contact pressure is more at the edges because of the edge stresses in clays. On the other hand, the contact pressure will be more at the center in sandy soil or granular soil because of the confining pressure effect. Therefore, the two soil clay, types of soils, clay and sand, show different behaviors. You should also know that contact pressure depends upon the depth of embedment. At shallower depths, the contact pressure is not generally uniform. On the other hand, at deeper depths, deeper elevations, contact pressure will be more or less uniform. So, whether it is sandy soil or clay soil. Well, friends, all this time we talked about bearing capacity, and bearing capacity is when the soil is likely to experience failure. You also may have a situation when more than failure, it is the settlement which governs the condition. Therefore, we should have an exposure to settlement. Soil is compressible. Soil is a three-phase system consisting of pore space, where it's very easy to expel out water or air, and hence cause settlement. We have to see to it that settlement is within limits, but we should be able to calculate settlement under different situation. So that's what we'll see now, how settlement is to be determined and what are the different types of settlements, and whatever settlement you determine, if it is within limits, okay. If not, we may have to think about some improvements. So settlement is the vertically downward movement of the ground, which in turn causes the vertically downward movement of the building, either partly or fully. Why will it happen? Because the ground is not rigid, it is flexible, and it is now stressed more because of the presence of the building, and hence the ground is likely to experience a volume reduction. You should know that this volume reduction can be divided into three different components. One is elastic component, another is consolidation component, and third one is creep. The elastic component is the immediate settlement, which happens in the first couple of hours or first couple of days. It is due to the elastic properties of soil. So basically, fundamental elastic properties like Young's modulus, Poisson's ratio play a role. Naturally, soil which is having more Young's modulus shows stiffer behavior, so settlement is less. On the other hand, lower stiffness, automatically settlement is going to be more. And it is the consolidation settlement which is predominantly causing settlement. Not all soils experience consolidation settlement. It's basically the clayey soils which experience consolidation settlement. And our job is to see that the settlements are within limits or compute the consolidation settlement, and that happens after elastic settlement. Later on, you also have creep settlement, which will be only after the ground has experienced complete 100% consolidation. Even after that, there will be creep settlement seen. There will be settlement which is beyond explanation possible. It's a long-term process. Not in all soils it is found, but that is also going to have some amount of settlement. Our job is to find settlement and see whether it is within limits or not. So as I said earlier, total settlement can be classified into three components: immediate, consolidation, and secondary settlement. SI stands for immediate or elastic settlement, SC for consolidation settlement, and SS for secondary settlement. As I said earlier, immediate settlement happens immediately, maybe in the first few days or first few weeks after the construction of the load is put. It is purely due to the elastic properties of the soil. It happens in all kinds of soils depending on their elastic properties. Some of them may be stiff, less of elastic immediate settlement. Some of them may be soft. It all depends. So as I said, it occurs immediately after the load is applied, and it depends upon the size, the elastic properties of foundation, soil. It depends on rigidity, size, and shape of the foundation. So, friends, I want you to remember this formula. So here bracketed term is the elastic property, 1 minus mu squared by E. SI, immediate settlement, is 1 minus mu squared by E into Q into B into I rho. I rho is called influence factor. It is a constant, and it depends upon how flexible the soil is and what is the shape of the foundation. E and mu are the elastic properties of the foundation soil, and then Q is the contact pressure at the base of the foundation. B is the width of the foundation. So you use this formula to find out immediate settlement. I want you people to be, exposed to a few questions. This is a very lengthy question. I read the question. A multi-story building with a basement is to be constructed, multi-storied building, also with a basement. Top 4 meters of soil consists of loose silt. Below this level, dense sandy layer is present up to great depths. Groundwater table is at the surface. The foundation consists of basement slab of 6 meters width, which will rest on the top of the dense sand as shown in the figure, which is in the next page, next sheet. For dense sand, saturated unit weight is 20 kilonewton per meter cube. NQ and N gamma are given. For loose silt, saturated unit weight is 18 kilonewton per meter cube. NQ and N gamma are given. Effective cohesion for both of these soils is 0 because it is sandy soil, cohesionless soil. Unit weight of water is 10 kilonewton per meter cube. Neglect shape factor and depth factor. Average elastic modulus is E, Poisson's ratio. Mu, both are 60 MPa and 0.3 respectively. The foundation slab is subjected to vertically downward stress equal to net bearing capacity about 100 kilopascal. Using an influence factor of 2 and neglecting embedment depth, the rigidity connection and the rigidity corrections, the immediate settlement of the dense sand layer will be dash. Please note that here a lot of redundant equations, redundant data are given. Whenever you want to find bearing capacity, of course, you require NC, NQ, N gamma, and the other factors like shape factor, depth factor. We are not finding that. We are required to find only the settlement. So, please use the formula here, immediate settlement. It is mentioned that, you have loose silt for a thickness of 4 meters. Below that is dense sand. The foundation width is 6 meters. Okay. It is being provided exactly at the interface. Now, in the formula, mu is known, given as 0.3. Young's modulus is known, it is 60 MPa or 60,000 kPa. Q is the contact pressure, and in this case, it is mentioned that the capacity it is subjected to is 100 kilonewton per meter squared maximum. Q is 100 kilonewtons. B is the width of the foundation, that is 6 meters. And hence, you will be in a position to use this formula and find the value of immediate settlement. And in this case, we found it to be 18.2 mm because Q is 100 kPa, B is 6 meters, Young's modulus is 60,000 kPa or 60 MPa, Poisson's ratio is 0.3. Friends, let's move to the next problem. A circular raft, 20 meters in diameter and 1.6 meters thick, is provided for a tank that applies a bearing pressure of 110 kilopascal on sandy soil with Young's modulus as 30 MPa and Poisson's ratio is 0.3. The raft is made of concrete. The values of Young's modulus and Poisson's ratio are given. Considering the raft as rigid, the elastic settlement is equal to dash. Please note that many of the data may be redundant here. Okay. You again have the formula for immediate settlement. E is given 30 MPa or 30,000 kPa. Mu is given, that is 0.3. Width of the foundation is given 20 meters. And Q, that is the contact pressure, is given as 110 kPa. Under these circumstances, you're going to find the immediate settlement as 0.06671 meter, or if you put it in millimeters, it would be 66.71 millimeters. Let's move on to the next settlement, consolidation settlement. You know, consolidation is a process which all of us are familiar with. A soil which experiences consolidation will experience huge amount of volume reduction, and it's going to cause settlement. Not all soils experience consolidation. Mainly it is the clay soil, and consolidation is a major culprit for huge amount of settlement. Let us try to see how you can compute this and how you can reduce the consolidation settlement to the best extent. So it occurs due to the process of consolidation. Clay and organic soils are the most prone to consolidation settlement. Consolidation is the process of reduction in volume of the soil mass. Why will it reduce? Because of the expulsion of water under increased load. So you cannot it's the reduction in volume because of the removal of water from it. It's a time consuming process. Okay, it takes long time for water to go out, and all the time which is required will be equal to how much time, how much distance water has to move to release the pressure. So it takes sufficient amount of time, and many a times people are likely to get confused between compaction and consolidation. I normally try to explain that compaction is a mechanical process. It is a fast process. Their volume reduction is because of the expulsion of air, not water. It is seen in a partially saturated or dry soil. It is not seen in saturated soil. On the other hand, consolidation, spring mass analogy is very ideal to explain consolidation, settlement, consolidation. This also volume reduction, but because of the expulsion of water. So this can be seen in only saturated soils, saturated clay soils, and it takes longer time for water to expel out. So we should have a good knowledge between about the two phenomena, compaction and consolidation. So what we are talking about is consolidation, and it happens in clay soil, it happens in fully saturated soil. The formula which you can use to determine consolidation settlement is something like this. You require the consolidation properties of soil. You require to know how much was the initial stress, how much is the final stress, and so on. You require to know what is the thickness of the soil which is likely to experience consolidation. So the equation for finding the consolidation settlement SC is equal to Cc over 1 plus C naught H into log 10 to log 10 of sigma naught plus del sigma divided by sigma naught. So here sigma naught happens to be the overburden pressure which is at the initial stage. If there is no surcharge, that is simply equal to the weight of the soil above. If it is uniform soil, if gamma is the unit weight, Z is the depth, then overburden pressure will be gamma Z. Delta sigma is the additional pressure also at the point of interest, which is due to the presence of new structure. So Cc is compression index, E naught is initial void ratio, H is the thickness of the clay layer, sigma naught is the initial overburden pressure, and delta sigma refers to the additional pressure due to the addition of new construction. So let me try to give you the problem to solve. Generally, problem related with the consolidation or in general settlement will be quite lengthy. Please take down the problem, understand the problem. A water tank is to be constructed on the soil deposit shown in the figure. You can see in the figure, water tank is to be constructed. See that it is made up of several layers of soil. There is groundwater table at 2 meter depth. The top layer is silty sand. Please note, silt or sand cannot experience consolidation. Therefore, there is no consolidation here. Below this, you have sand for 6 meter depth. Below that, you have 10 meters of clay soil. 10 meters of clay soil. The properties are given. Silty sand, bulk unit weight is given. Sand, saturated unit weight is given because it is underwater. And for clay soil also, you have the data like, saturated unit weight is given. And then, compression index is given. Initial void ratio is given. Coefficient of consolidation also is available. This is the equation which I suggested you. Possibly you may have to memorize this. And based on what is given here, I'll read now. A water tank is to be constructed on a soil deposit shown in the figure. A circular footing, diameter 3 meters, and depth of embedment 1 meter has to be designed, and it should be put on the ground supporting the tank. Total weight, the vertical load which is to be taken is 1500 kilonewtons, 1500 kilonewton. Assume unit weight of water as 10 kilonewton per meter cube. And the load dispersion curve, it all depends upon the type of the soil. And in this case, you can assume that it is 2 vertical to 1 horizontal. So you need to find out the expected settlement. How much is the settlement? And consolidation settlement, this is the equation which is given. Cc is compression index, which is given 0.3. E naught is the initial void ratio. Please note that initial void ratio is given. Basically, one thing you should understand is that top soil is silty sand for 2 meters. Below this, for 6 meters, you have sand. Sand is not going to experience consolidation. It's only clay soil. That too when it is fully saturated. You see that groundwater table is here. So only the clay here for a thickness of 10 meters is likely to settle. It is in saturated condition, normally consolidated. If it were to be over consolidated, settlement would have been less. And then you have dense sand below, which is also not going to settle under consolidation. So only the third layer is likely to experience consolidation, and you need the data for that. So Cc is given as 0.3, initial void ratio is given E naught, thickness is 10 meters. Sigma naught happens to be the initial overburden pressure, and we try to find the average. Therefore, we try to find the settlement at the middle of the clay layer. So you find out sigma naught at the middle of the clay layer. All density is known, 15 into 2, and then plus 18 into 3, 18 into 6, and then this 18 into 5, it is known, and keeping all that, sigma naught you get as 118 kilopascal. Then del sigma is the additional load due to the presence of the water tank. it is mentioned that the total load is 1500 kilonewtons and it is being spread uh, you know okay, the load is acting like this, okay, and the footing is 3 meters wide, and this is the center of the clay layer. It is mentioned that load dispersion is at this angle, like this. What is this angle? It is given as one horizontal to two vertical. Okay, so 1500 kilonewtons is spread over this much area. This is 3 meters, and this is over a length of 2 plus 6 plus 5. 2 plus 6, 8 plus 5, 13. Okay. So at 2 is to 1, this will be 6.5. Again, here also, one mistake I did was, it is not at 2 meter depth. The foundation is put at 1 meter depth here. Foundation is put at 1 meter depth. So this is 1 plus 6, 7 plus 5, 12. Therefore, this is 6 meters. This is also 6 meters. This is 3 meters. 6 plus 6 plus 3, 13, 15 meters and 1500 kilonewton. So it is now having a diameter of 15 meters. I need to consider del sigma based on this 1500 into pi by 4 d square. So 8.49 is del sigma. And then sigma naught is known, Cc is known, E naught is known, H is known. All things known, you only have to find out Sc, and you find that the settlement is equal to 53.2 millimeters, and this is only by direct computation. Let me take you on to the next problem. A 4 meter thick layer of normally consolidated clay has an average void ratio of 1.3. The void ratio is 1.3. Its compression index is 0.6. So here, friends, you know the void ratio, you know the compression index, and the thickness of the clay layer is also known 4 meters. It's also given that coefficient of consolidation is 1 meter squared per year. The increase in the vertical pressure due to the foundation load on the clay layer is equal to existing effective overburden pressure. Effective overburden pressure was sigma naught dash earlier, and delta sigma is the increase in the pressure due to the new structure which is being built. It is mentioned that this increase is equal to initial overburden pressure. So delta sigma is equal to sigma naught dash. Therefore, this total ratio is going to be equal to 2. Equal to 2. So substituting all these things, you get the value of Sc as 314 millimeters. Therefore, answer is B. Please do take this problem, understand this problem. You have a layer of sand 1 meter thick, layer of clay also 1 meter thick below the sand, and groundwater table is at the top of the clay layer at 1 meter below the ground. An undisturbed sample of soil was taken from the middle of clay layer. So from the middle of clay layer, from here, undisturbed sample was taken. Water table was up to the top of the clay layer here. Laboratory test results show that water content here was 25%. Pre-consolidation pressure 60 kilopascal. Compression index 0.5. Recompression index is 0.05. Specific gravity 2.7 of clay is 2.7. Bulk unit weight of sand is 17 kilonewton per meter cube. And on top, a compacted 2.5 meter high compacted fill having unit weight of 20 kilonewton per meter cube is to be placed on the ground level. Here at the ground level, you have to put a 2.5 meter high embankment whose density is 20 kilonewton per meter cube. Assuming the unit weight of water as 10 kilonewton per meter cube, ultimate consolidation settlement in millimeters is given as dash. Again, you need to think of this equation. CC is compression index. It is given as 0.5. Next, E naught is the initial overburden pressure. It is not directly given, but the specific gravity is given. The water content is given. Fully saturated, therefore Wg is equal to S into E, where S is equal to 1. Therefore, E is equal to W into G. W is water content 0.25 or 25%. G is 2.7. Therefore, void ratio you get as 0.625. H is the thickness of clay layer, that is 1 meter, this thickness. And sigma naught dash, sigma naught is the initial overburden pressure. So pre-consolidation pressure of clay is given, that is how much it has been consolidated, that what pressure. The pressure is found to be 60 kilopascal. Otherwise, you could have been given the density, it is not given. Instead, the pressure it was subjected to before was 60 kilopascal. And del sigma happens to be the new pressure which is created. And that new pressure is created by 2.5 meter high embankment having 20 kilonewton per meter cube as the density. So 20 into 2.5 will give you 50. So sigma naught is 60 and del sigma is 50, and that's what I have written here. Based on this, you find that the consolidation settlement has some value, 78.6 millimeters. So friends, this is how you can determine the consolidation settlement, and this is one of the popular equations, and I would like you to perhaps remember this. That is the best thing you can do. Remember this equation. SC, consolidation settlement, is equal to CC over 1 plus E naught H into log base 10 of numerator sigma naught plus del sigma, denominator is sigma naught. Let's go to the next settlement, secondary settlement. Even today, we do not know exactly what are the reasons for secondary settlement. It is the readjustment of equilibrium position which the soil at site experiences, which causes secondary settlement. It happens only when the primary settlement is completely over. It doesn't happen in all soils. Perhaps organic soil, highly sensitive clays experience the settlement. The formula for secondary compression is it's basically also called creep. Many a times we call it as creep settlement. The formula for this is C alpha, which is the coefficient of secondary compression. It depends upon the type of the soil. H, thickness of this clay layer. So it happens only in clay soil, not in silts, not in inert materials like granular soil. Log to base 10 of. In the numerator, you have time taken for secondary settlement minus time taken for primary settlement. In the denominator, you have time taken for primary settlement. You might ask me, what is the time taken for secondary settlement? It will keep on, infinitely. So you can put the lifespan of the structure as time taken for secondary settlement, maybe 60 years, 100 years. Time taken for primary settlement, maybe primary consolidation to be over. It can happen, in the field for 1 year, 2 years, 3 years. It all depends. As long as the pressure is high, as long as scope for water to come out is less, it takes time. So all these things known, C alpha, H time secondary, time primary, you can find out the secondary compression. If I try to plot a graph between settlement and time, you will notice that during during consolidation, there will be considerable amount of settlement which is happening. And once consolidation is over, strictly there should be no settlement, but gradually there is still settlement which is happening. So this point is the end of consolidation. So secondary settlement will start only from them, and not in all soils. You will see the settlement happening further in with increase in time. In majority of the cases, the graph becomes horizontal, indicating that there is no secondary settlement. Only in a few soils you will see that slope of this line will give you the coefficient of secondary consolidation. Normally, secondary C alpha is different for different type in different type of soils. In a highly over consolidated clay, the value is less. On the other hand, in normally consolidated soils, the secondary compression is sufficiently large. In organic clay, it's also found to be sufficiently large. So based on this, we can take one more problem related to creep or secondary settlement. Determine the creep settlement in a sensitive clay of thickness 6 meters. Thickness is given 6 meters. C alpha is given, that is coefficient of secondary compression. When the laboratory sample 20 millimeter thick with double drainage experiences complete consolidation in 10 minutes. So you have a laboratory specimen, okay, which experiences double drainage. That means, you have a porous stone at top, you have a porous stone at bottom. Okay. So the drainage is double. That means, the water can travel maximum distance, okay, equal to the thickness by 2 of the clay layer. So time taken in the laboratory for small specimen is 10 minutes. But how much time is taken in the field for 6 meter thick? It is given here. 6 meters is 600 mm. Okay, 600 mm. And then 20 by 2. So it is 10 into 600 by 20 by 2 whole square, amounting to these many minutes. And time taken for primary consolidation will be these many years. Time taken for secondary consolidation, you can assume that the lifespan of the structure is 100 years. You can take that. C alpha is known, H is known, time for secondary settlement is known. Therefore, you have to find out the secondary compression, and the value is found to be 0.068 or 68 millimeters. So here also you are required to remember this formula. You also have to remember that, the ratio of time taken in the lab to field is proportional to the ratio of drainage path to the power 2. Remember that. Friends, now it is time for us to go to pile foundations. Remember, pile foundations form deep foundations. You call a foundation as deep when the depth of foundation is much, much larger than the width of foundation. So let us move ahead. Pile is a very popular deep foundation. Normally, construction wise, you can call the the two different types of construction are, one is bored pile and another is driven pile. What do you do in bored pile? You make a borehole, insert the reinforcement cage, and fill up the concrete. Many a times when you make a borehole, there is a likelihood that soil may collapse. To avoid it from collapsing, you put a liner. The collapse may happen because the soil is loose, because there is groundwater which may push, so to take care. Bored pile cannot be taken very deep. Maximum it's about 20 to 25 meters depth. You take the bored pile. The other type of pile is driven pile. You drive a pile exactly in the similar fashion as you drive a nail into the wall. Normally, you drive a nail horizontally into the wall. Nail has got a sharp edge at the bottom, and then a head at the top, so that you can hammer it. Exactly in the same way, you're going to drive a pile, but in vertical direction, on the ground. So you place the pile on the ground. At the bottom, you have sharp edge, and you also have the uh, edge, which is tough, made out of tough steel. And then at the top, you have a helmet or a cap before hammering, and you hammer from the top till the pile reaches its desired depth. It may be 10 meters, 20 meters, 30 meters. There is no limit for that. You keep on hammering it. So that's a driven pile. So here in the picture, you see, a pile being driven here, here also. This is pile already being put, and people are waiting for the pile cap to be put. From there onwards, the superstructure is taken up. Piles can be very broadly classified into two types of piles based on the load carrying capacity. One is end bearing piles. These are the piles which take the entire load, at the bottom, just like shallow foundations. So if there is some load which it has to carry, because there is not much of friction between the soil and the pile in this soil, weak soil, no resistance, and entire resistance comes at the base. So that is a end bearing pile. It is also called socketed pile because this pile is taken deep into hard soil, okay, which looks like it is being socketed. On the other hand, the other extreme case is when you put the pile foundation to take the load mainly near the sides here, mainly near the sides here. So at the tip, at the end, it is not going to take any load. So the load is taken because of the friction that exists between the soil and the pile here. Therefore, the area of the soil, the area of the pile exposed to the soil will play an important role, and the permissible stress which it can take. So such piles are called friction piles. So friction piles take load only through the friction on the skin of the pile. On the other hand, end bearing pile carries the load at the tip, at the base. So friction piles are also called floating piles. You should remember that total load carried by pile is equal to load which is carried at the tip or at the base plus load which is carried on the skin. So P is equal to P1 plus P2. P1 happens to be the load carried on the skin. P2 happens to be load carried at the base. So the same thing I have mentioned here. So whatever P1 I have expressed as QP at the base, at the point, and QS along the skin. So total pile load is equal to the load carried at the end plus load carried along the skin of it. You should understand, you have a pile, you start applying the load. When the first load, small load is applied, initially the load is carried along the skin, along the top portion. And when the load is increased, then slowly shear is mobilized in the other parts of the pile. So this is how the pile load transfer takes place initially, and it keeps on increasing like this. And only when complete load carrying capacity on the frictional point is over, the tip becomes important. So then the load carrying capacity from the tip side increases. So this is how the load transfer mechanism is for pile foundation typically. One of the important requirements of pile foundation is to find its capacity, how much load it can carry. And as I mentioned earlier, the total load it can carry is equal to load it can carry along the surface plus load it can carry at the base or tip. So QU, ultimate load carried by the pile, is equal to QP, point resistance at the tip, plus shaft resistance along the skin, along the surface of the pile. So ultimate bearing capacity is equal to skin friction plus end bearing. So this is end bearing QB and this is skin friction QS. So how do you find the load carrying capacity? You can find it by different methods. One such approach is by static formula. So what do? You take the basic properties of soil and try to compute. So Q is equal to QS plus QP. QS is the load carried along the surface. QP is the load carried at the tip, at the point, base point. And that QS is equal to the stress, permissible stress QS into area. QP, permissible capacity at the base into area AP. Q is the total capacity. QS is the maximum stress the soil can bear. And QP is also maximum stress the soil can bear at the base. Area of the surface and also area of the point, area of the tip are given. So you have to determine the capacity. So only thing which is big challenge is, how do you find the permissible stresses or how do you find the stresses carried? So in purely cohesive soil, the the ultimate stress is equal to the capacity, that is cohesion. But many a times ultimate value may not be reached because complete shear may not be mobilized. Therefore, QS can be considered as alpha times Cu. Alpha is the shear mobilization factor, which depends upon several issues, and that can be taken as around approximately 0.7 or 0.8, and it depends upon the type of the soil also. QP is the tip resistance. Because it is purely cohesive soil, it is independent of the overburden and independent of the type of the soil. Therefore, the second and third terms of bearing capacity vanish there. NQ is not there, N gamma is there, not there. Therefore, QP is going to be NC times Cu. Okay. So if you know the underlying strength of the clay soil, then QP can be determined from that. If it is the other extreme, completely sandy soil, QS will depend upon how much is the confinement. And you know that the confinement, the horizontal stress is equal to vertical stress multiplied by K0, which is the coefficient of earth pressure. And the vertical resistance will be equal to, this is the normal force perpendicular to the plane into tan delta, where delta happens to be the friction between the soil and the pile. And hence, delta is close to phi friction angle, or sometimes it may be lower also. It all depends. So QS is K0 into gamma L by 2 into tan delta, whereas QP is equal to 0.3 or 0.4 gamma Bn gamma. Okay. So this is how you find out the pile carrying capacity. Friends, I have also talked about shear mobilization factor. Some people use the symbol M, some people use alpha. Complete shear strength may not be mobilized under all circumstances. So, only a part of it may be mobilized, 30%, 40%, 50%, 60%. It depends upon the type of the soil also. And closeness of the neighboring pile And geometry of the pile system also plays an important role for that. So shear mobilization factor is quickly found out depending upon the type of the soil, and it will be indirectly equal to the efficiency of the pile. So if the soil has some capacity, like let us say 80 kPa over unit area, then shear mobilization factor will let you know that the capacity is 80, but that full shear mobilization is not achieved. That value will be lower. The maximum capacity, maximum you can take will be lower because of the factor, this factor to be considered. Friends, you can determine the capacity by static formula, as I said. You also can determine by dynamic formula. What do I mean by dynamic formula? I told you that there are two types of piles. One is driven pile. What do you do there? You drive the pile. How do you drive the pile? You drive it from the top, hammering. If the resistance is more, then you have to apply more driving force. And automatically, you know that the capacity is high. On the other hand, if the driver can penetrate very quickly, it indicates that the soil is softer. Therefore, we may be in a position to use the driving energy to determine the capacity of the soil, and this is called dynamic formula. So whatever energy is required, it is the work done basically. Work done is WH, and to that work, the pile will experience some settlement. If the applied load is more, automatically the energy is more and the penetration also will be more. So basically, capacity is load carrying capacity, which is multiplied with the penetration. So in a very simple term, WH is equal to QU by S. QU is the capacity, and hence that's what you need to find out, WH by S. But you require the allowable load, and hence you have to apply a factor of safety. And the kind of force applied for driving, it depends on several things. Therefore, there is some factor which has to be taken into account depending upon the type of the driver used. Therefore, the formula which we use is Q allowable. It is not QU, it is Q allowable is equal to WH by factor of safety into S plus C, where S happens to be the final penetration per blow, C happens to be the empirical constant which is used. Okay, and that empirical constant will depend upon the type of the hammer. If it is drop hammer, you can take this value as 25 millimeters. If it is single acting hammer, you can assume it to be 2.5 millimeters. Therefore, when you know the weight, when you know the height of drop, you may be able to approximately determine the capacity. And engineering news formula is one of the standard formulae because of its simplicity. However, in IS code, you will see this formula, which is called a Hiley's formula. You see that in IS 2911. Okay. According to this, the capacity, ultimate capacity, is given by this formula. So this is more involved. It has got eta horizontal, it has got eta base, and then you have S plus C by 2. Okay. So eta H, eta B, the two efficiencies, efficiency of hammer and efficiency of the base, will indirectly give you the efficiency of the pile. It lets you know the efficiency. So QD is the ultimate load carrying capacity. C is the total elastic compression, which is a combination of C1, C2, C3. C1 happens to be the elastic compression of the packing material. C2 happens to be 5 for the pile, C3 happens to be for soil. You need to take all this into account. Eta H is the efficiency of the hammer, and eta B is the efficiency of the blow, which depends upon the impact the hammer makes with the pile. I have just tried to summarize the advantages of dynamic formula. As I said, it is applicable only in driven piles, but because when you drive the pile, you're going to use the hammer, you're going to see the penetration resistance, and if more hammer force is required, naturally resistance is high, capacity is high. Otherwise, you will directly be able to see the capacity based on that. So what are some of the important comments about dynamic formula? Please note that it is best suited for granular soils, okay, not for clay soils, where the shear strength is, dependent on several factors, including rate of loading. The relationship between dynamic formula and static form and dynamic and static capacity is very difficult to make. Lot of unpredictable things in dynamics, and whatever you do in driving the pile is dynamic force which you apply, but what we want is the static capacity. Many people question whether you can relate these two. Then saturated loose fine sand will liquefy many a times whenever it is subjected to heavy dynamic force due to the development of excess pore water pressure. And on the other hand, if it is dense sand, there may be negative excess pore water pressure situated or developed. We have to take that into account. And in clay, mobilization of skin friction takes a long time. So you try to do the test while driving, but capacity will increase with increase in the time. So it is always contradicting, because driving is done for maximum few hours. Therefore, the shear mobilization may not have happened by then. There is no indication about settlement here. We don't talk about settlement. We only talk about the capacity. You don't consider pile group here. You only consider one individual pile. And there are many losses you need to consider here. And these losses are difficult to predict. So these are some of the important, comments on dynamic formula. So, well, friends, you are required to know that pile foundation does not involve only single pile. A number of piles at the top are connected by a pile cap, single pile cap. On top of the pile cap, the structure is built. So it is a group of piles which you consider in the design. Sometimes, if it is a simple situation, there are only 2 piles which are required. It may be 3 piles, it may be 4 piles, it may be in multiples of 10 or multiples of 100 also, depending on the load which is coming. So you want to know the capacity, and you should know that the capacity of individual pile, which we already determined, multiplied by the number of piles, will not give you the total capacity. Total capacity will usually be less than the capacity of single pile multiplied by number of piles. So you use a group efficiency here, eta G here. You use a group efficiency here, where N is the number of piles used, Q is the capacity of individual piles. And this group efficiency depends upon several things: the geometry of the pile groups, number of piles, and so on. And only then you should be able to find out the capacity. How the piles are arranged in plan: if you have only 2 piles, very rarely you will have only 2 piles. And if you have only 2 piles, you're going to arrange them together like this and single pile cap. If it is 3 piles, you arrange them like this: 4, 5, 6, 7, and so on. You arrange in whatever fashion you want. This is how piles in group are arranged. Then you're going to put them together, and there will be some specific spacing between them. When the spacing is small, you require more number of piles, but there is a likelihood that they overlap, and hence capacity is reduced. When the spacing between them is very large, then you see that the interaction between the piles is less. They act independently. You need that interaction also. So there is a need for that coordinated effort. So 2 pile, 3 pile, 4, 5, 6, etc. pile systems are given. And how do you find out the efficiency? You can use the geometry. This is one formula which is popular, Converse-Lebare formula. So according to this, the capacity is dependent upon the geometry. Theta happens to be the, D is the diameter of the pile and S is the spacing. So this is D and S is from here to here. This is S. Okay. Theta is equal to tan inverse D by S, and M is the number of piles in a row, and N is the number of rows. So for instance, if you have 1 pile here, 2 pile here, 3 pile, 1, 2, 3, there are maybe 4 rows. Then number of piles in a row M is equal to 3, and number of rows N is equal to 4. Okay. And hence, spacing is known, diameter is known. You can find out eta G. So group efficiency will always be less than or at the most equal to some of the individual efficiencies. No effect on end bearing effect, end bearing. It's only in the frictional one. So all these group efficiency is affected due to the frictional effect. I'm always impressed by this Felt rule. What does it say? It simply says that because of the interaction with the neighboring pile, reduce the efficiency by 1/16th of its capacity. When the piles are too far away, maybe don't take this rule. When they are close by, you take this. No other calculation. So, for instance, if it is a 3-pile system, then the efficiency will be each of these 3 piles is affected by the neighboring pile. Therefore, it is, this is one pile which is affecting, this is the second pile which is affecting. So there are 2 such piles which are affecting, and each effect is 1/16th. So you're going to take only 14/16. There are 3 piles both at numerator and denominator, and hence efficiency is determined. Let us take this case where there are 9 piles. Then if you take these corner piles, these are affected by 1, 2, and 3. If you take the side piles, then these are affected by 1, 2, 3, 4, 5. On the other hand, if you take the central pile, you will be taking the effect of all the 8 piles. So considering these, you have totally 9 piles. You have totally 9 piles here. 4 are affected by 3, therefore 4 into 13/16. 4 are affected by 5, therefore 4 into 11/16. And then 1 is affected by, affected by the effect of 8 piles, therefore 8/16. So you find the efficiency. So you can find efficiency using Felt rule when you don't want to memorize. Friends, I would like to talk about this aspect, negative skin friction. What is negative skin friction? Skin friction, you already know, this is the one which resists the load. It adds to capacity. Sometimes this resistance will be opposite. This is negative. That means it is not going to increase the load carrying capacity, it's going to decrease. It is going to have a negative effect. So the effect of this is to reduce the load carrying capacity. You have to take a note of it carefully in the design. If you make a mistake, you're going to be on the other side, not on the conservative side, and it might cause a huge disaster. You have to be very careful. You can see this type of effect in filled up soils which are likely to experience large amount of compression. You might see in organic soils or even peat, which also are likely to be compressed. When there is a sudden groundwater drawdown, then also effective stress is going to increase. It's going to collapse in highly compressible soft soil, or when the surcharge is heavy, when there is a heavy surcharge. So these are all the situations when you go in for negative skin friction, and we have to very accurately determine that, identify that, and incorporate that in our design. You know, plate load test is carried out to find the load carrying capacity of shallow foundations. Very similar to that pile load test is carried out to determine the load carrying capacity of piles. So conventionally, just like plate load test, you're going to apply more and more load. There is a base plate at the bottom, and there is the pile which is put, and you keep on applying the load either until it fails or until the mm, you know mm, settlement happens considerably. So what is done here, you either take the working pile, the pile which will be used later on for the construction, or you do that on a test pile which will be removed or replaced afterwards, or maybe which is just discarded as it is. And you have the pile here, you have a platform, and on the platform you're going to place heavy weights like concrete blocks or maybe sandbag like, a bag like this, and keep on doing it till failure is reached. So this is the other type of picture which talks about pile which is being tested. On either side you have the support, and hence you have a regular platform, and then load is applied. This is reaction loading, and you can see that a truss is there to take the reaction, and there is a jack. It's going to push, and the truss is going to have an indirect downward force. So just like in plate load test, you plot load settlement curve here also, and this is a typical load settlement curve upon loading, upon unloading, and you find out finally that the estimated load is half to one third of the final load, which causes 10% settlement equal to 10% of the diameter of the pipe. If a pile is of 500 diameter, then whenever you get 50 of settlement, you find out the load, half of that load will be the allowable load, or two-thirds of the final load, which causes a settlement equal to 12 So you can take either of the two, or two-thirds of the load, which causes net settlement of 6 So total settlement will be some value, and once you release the load, it will get back to original, may not be to the original portion, somewhere. So net capacity, net settlement, if it is 6 millimeter, whatever is the load is taken, if that is P, two-thirds of P will give you the load carrying capacity. So friends, you should remember, The load carrying capacity is determined by four methods: static capacity, dynamic capacity, pi load test, and also by the other you can say by other indirect tests like SPT or some other methods penetration resistance tests. So here I taught you three methods: static capacity, dynamic capacity, and from pi load test. Let us try to solve the problems, and maybe I'll take you on to the first problem. A pile of diameter zero point 0.4 meter is fully embedded in clay, having five layers. So you have clay, of five layers, each of 5 meters. And each of this clay has its shear parameters: shear capacity of C equal to 40, 50, 60, 70, 80 kilonewton per meter square. You are assuming that the unit weight is constant at 18 kilonewton per meter cube. The average adhesion factor is 0.25 for the total 25 meter length. Neglect end bearing. You only find out the pile capacity considering the skin friction. So pi into d, perimeter d, into length, total length, okay, into alpha, into cohesion. So cohesion is not uniform. So you can take the average value, or what you can do is pi d into L1 into alpha into C1 plus pi d into L2 into alpha into C2 plus pi d into L3 into alpha into C3, and so on. And from that you get the capacity as 471.2 kilonewtons. So it is just cumulative. For every 5 meters, you find out for depending on the cohesion. Maybe friends, it's already time. Therefore, we'll quickly go through the next few questions. The action of negative skin friction on the pile is, what does negative skin friction do? It's going to reduce the capacity. To increase the ultimate load? No, it doesn't increase. Is to maintain the working load? No, because of negative skin friction, capacity reduces. Is to reduce settlement? No, 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 no. So settlement, we are not talking about settlement in case of capacity here. Therefore, it is B. It is to reduce the allowable load carrying capacity. Load carrying capacity decreases. Therefore, we have to be very careful. We should not be taking any risk when there is a possibility of negative skin friction. So here you have the other question. Two identical concrete piles having the dimensions 50 it's given in centimeters, don't mistake, okay, 500 mm by 500 mm, are driven into homogeneous sandy layer as shown in the figures. Okay, in one of these you have dry sand, in the other you have saturated sand. Consider the bearing capacity factors as NQ equal to 24 for phi equal to 30 degrees. If QP1 and QP2 represent the ultimate point bearing resistance under dry and submerged conditions, which of the following is, a appropriate statement? So this is QP1 and this is QP2. In the difference between these two is, in QP1 there is dry sand, and here it is saturated sand. Once it is saturated sand, what will happen to the situation? You have to take the submerged density, submerged unit weight, and always submerged unit weight is approximately half the saturated or bulk density, bulk unit weight. Therefore, the capacity is reduced by 100% in QP2. So QP2 is less than QP1 by a margin of about 100%. I'm going to stop here because I wouldn't like to take the class beyond the limit. I just would like to mention to you that today we talked on a varieties of issues. To start with, I was talking about different types of foundations, from the isolated footing to combined footing to raft foundation. What are the requirements for providing raft foundation? And then we talked about contact pressure, we talked about settlements, we talked about three types of settlements: settlement which is immediate, which is also called elastic settlement, consolidation settlement, and then finally we talked about creep settlement. And after that, we talked about pile foundations. What are the different types of pile foundations based on the construction aspect? And also we talked about finding the pile capacity by static dynamic method, and also by using pile load test. So we talked about group efficiency of piles. We talked about how to compute the efficiency of the piles. With this, friends, I close my lecture. Thank you very much.
Thank you very much, sir. I'm sure that everyone has taken the note of the foundations like mat foundation and pipe foundation, which you explained thoroughly. And without any further delay, I take this opportunity to thank our beloved HOD, Dr. S.K. Prasad, for the wonderful session on foundation engineering. Thank you. Thank you very much, sir. And please kindly note that the second session of engineering hydrology would be starting exactly on time at 3:45. So thank you. Thank you everyone. Stay tuned.